Hi everyone. In this video, we'll be discussing Chapter 7, which is on confidence intervals. So we've got 4 sections to discuss here. In 7.1, we're going to be talking about confidence intervals. That's what CI means. Confidence intervals for the mean when sigma is known. 7.2, we'll talk about the same thing, but for when sigma is unknown. And then in 7.3, we'll talk about confidence intervals for proportions. Which is the binomial stuff, essentially. And in 7.4, we talk about confidence intervals for variances and standard deviations. Okay. So let's discuss 7.1. Here we'll define what a confidence level and confidence interval means. Let's start with that. So the confidence level of an interval estimate of a parameter is the probability that the interval estimate will contain the parameter. Okay, so when we're measuring or talking about the confidence level of something, we're going to be a certain percentage confident of that thing. We'll be 90% confident that the interval is between these, or that the parameter is between these two bounds, 95% confident that it'll be in there, 99% confident that it'll be in there, something like that. And so a confidence interval is a specific interval estimate of a parameter determined by using data obtained from a sample. And so that's pretty much the important things that we'll be talking about in Chapter 7. We're going to be looking for confidence intervals which will tell us the bounds that we need to be between in order to guarantee that percentage. So if we want to be 95% sure that something happens, or 99% sure that something happens, it's going to influence those boundaries. So let's first talk about the formula for a confidence interval of the mean when sigma is unknown. That's the first formula we'll discuss here. Okay, so the formula for the confidence interval for mu, aka the mean, when sigma is known, is x bar plus minus z star times sigma over square root of n. This will give us the upper and lower bounds of the confidence interval depending on what confidence level we're looking for. And this z star value it comes from whatever confidence level we're using. So z star is 1.65 for a 90% confidence interval. It's equal to 1.96 for a 95% confidence interval. And it's 2.58 for a 99% confidence interval. So try to memorize these ones. These ones get used quite often over and over and over again. And then we just plug it all into the formula. And this will give us, say it's a 90% confidence interval. Once we find the upper and lower bounds, we can be 90% confident that the true mean is in that range. So essentially here we're looking for the mean of a population. But all we know is the standard deviation of the population. What we can do is figure out what the mean is with some level of confidence, and that's what we're doing here. And there are some stipulations here. Number one, the sample needs to be random. And number two, either the sample size, n, needs to be greater than or equal to 30, or the population is normal when n is less than 30. So if we have a sample but it's less than 30, we have to at least know that it's a normal distribution before this stuff applies. Okay, so I've got an example here. A researcher wishes to estimate the number of days it takes an automobile dealer to sell a Chevrolet Aveo. So he wants to find the average number of days it takes to sell a Chevrolet Aveo on his lot. He takes a random sample of 50 cars and finds they have a mean a random sample of 50 cars had a mean time on the dealer's lot of 54 days. Assume the population standard deviation to be 6 days. Find the best point estimate of the population mean and the 95% confidence interval of the population mean. The best point estimate of the population mean in this case is x bar. It's basically this formula right here is the estimator plus or minus the margin of error. And so since we don't know what the true population mean is, our next best guess is the mean of this sample. And so that's why x bar is technically what is referred to here as the point estimate of the population mean. Don't need to worry too much about that. Okay, so this is very powerful. Let's just consider again what we're doing here. The researcher is wishing to figure out the population mean of the number of days it takes an automobile dealer to sell a Chevrolet Aveo. So he's going to figure out with a certain level of confidence the mean of the entire population from a single sample. It's really, really important. It allows you to, rather than actually figure out the mean, which would be very time consuming, very expensive, there'd probably be a lot of error involved. We can find the mean by looking at a sample and have a certain level of confidence that that's the actual mean. So we sacrifice a little bit of accuracy, I guess, for ease of calculation in a way. Okay, so what are we looking for here? Find the 95% confidence interval of the population mean. So we want to figure out what is the mean here with 95% confidence. We might be wrong, but we'll be 95% sure that it will be in there. And so it just depends on the level of confidence that the researcher is looking for in a way. So we're looking for that here. And remember the formula for, well, let's just pick out everything we know here. We've got a random sample of 50 cars. That's our n. So n is greater than or equal to 30. We know that's a big enough n to apply all this information. And it says that they had a mean time on the dealer's lot of 54 days. So what is that telling us? Remember, you basically just need to know what symbol this refers to. So what's the mean of a sample? What's the symbol for that? Remember, it's x bar. So that's our x bar. It's 54. Assume the population standard deviation to be 6 days. Okay, what's that? The population standard deviation, that's sigma. So we know sigma to be 6. And now we've got everything we need here for the formula, right? It's x bar plus minus z star times sigma over square root of n. So what's our z star here? Since we're doing a 95% confidence interval, remember z star for a 95% confidence interval is 1.96. And so now we do have everything for the formula. Remember, it goes 1.65, 1.96, 2.58. Those are the three numbers you really want to remember. A 90% confidence interval, the z star is 1.65. The 95% confidence interval, the z star is 1.96. The 99% confidence interval, the z star is 2.58. So plugging everything in here, we get 54 plus minus z star, that's 1.96, times sigma, which is 6 over the square root of n, that's square root of 50. I usually like to calculate the part after the plus minus. and then add and subtract it from the point estimator, which in this case is 54. So I'll go to the calculator. 1.96 times 6 divided by square root of 50. We get 1.663. Let's just round to 3 decimals here. This is fine because we're going to round for our final answer anyway, so we can do it here because there's no more calculations after this point, like for it to propagate through or anything. So we just do 54 plus this value, 54 minus this value. That's our upper bound, 55.663, and our lower bound, 54 minus 1.663, 52.337. So we get 52.337 is our lower bound, and our upper bound is 55.663. So essentially, so this is our answer. Let me just kind of draw a picture of what's going on here. Okay, so essentially what we've got here on the left, 52.337. And on the right here, 55.663. And essentially we're 95% sure that the mean is going to be between these two values. That's pretty much what we're doing here. So, this is very important in like risk analysis, things like that. It all just depends on your level of accuracy that you really want, I guess. Right, if you could be 99% sure of something, but in that case, you're just going to have really, really big boundaries, and it may not tell you all that much. So you might want to shrink it at some stages. You might want a 95% interval, 90% interval, et cetera, just to narrow the bounds a little bit and give us a little bit better of a guess. But it's more possible that it would be wrong to assume that it would be in there. Okay, let's try another one. So it says here, a large urgent care center with 4 doctors found that they can see an average of 18 patients per hour. Assume the standard deviation is 3.2. A random sample of 42 hours is selected. Find the 99% confidence interval of the mean. Okay, so let's pick out everything we've got. It might be tempted for you to pick n to be 4 here. I guess that 4 is a bit of a superfluous bit of information. Doesn't really matter how many doctors they had. So that 4 might throw you off. But it says that they see an average of 18 patients per hour. That would be our X bar here. Assume the standard deviation is 3.2. It should have said population. I wish it said population there. I hate when they're ambiguous like that. because the entire next section is when we don't know the population standard div. So I guess we have to know the population standard div here because we're not in that section yet. But they should have said that here anyway. And a random sample of 42 hours was selected. That's our N. And we're looking for a 99% confidence interval, which lets us know that the Z star for our formula is 2.58. Okay? And this will give us the intervals that will be 99% sure that the actual true mean is between. Remember, our formula is x bar plus minus Z star times sigma over square root of n, giving us 18 plus minus 2.58 times 3.2 over square root of 42. Again, I usually put in my calculator the part on the right side of the plus minus. So 2.58 times 3.2 divided by square root of 42. So this gives us approximately 1.274. So we just subtract and add this from 18. 16.726 for our lower bound. And 19.274 for our upper bound. So what we've learned here is that the true mean of the population, not just the sample, we're 99% sure that the actual average of how many patients, an urgent care center with 4 doctors would see would be between 16.726 patients and 19.274 patients. Okay, so it is possible that you'll have to find a Z star for a different level of confidence than the 3 that we usually use. So let's talk about that for a sec. So let's examine the Z star for the 90% confidence interval. I know we already know this one, but I want to show you guys how we end up getting those numbers, and then that will inform you how to find the other ones as well. So if we want a 90% confidence interval, that means we want this inner value, this inner area rather, to be 90% of the data, right? AKA 0.9. 90% or 0.9. Well, if this accounts for 90% of the data, how much of the data would be in the 2 tails? Well, remember, it is symmetrical, so if the middle is 90%, that means we've got 10% left to divvy up amongst the tails. So that would mean that this tail would have 5%, or aka 0.05. This tail would have 5%, aka 0.05. So you can look at it as percentage or probability, right? The percentage is above the probabilities here in what I've written. And so if we want to see how to find this cutoff value, what's going to be the area to the left of this? It's 0.05, right? And remember, our Z tables tell us the area to the left of a specific Z score. So that's what we're going to be looking for here. We want to find what z-score produces an area to the left of it being 0.05. So we look for the closest z-score to an area of 0.05, and that will give us this one. And the one on the right is just the positive of that z-value, right? Since z-values are symmetric, the positive is the right half, the negatives are the left half. If we find a negative z-score on the left half that has 0.05 to the left of it, the z-score on the right with 0.05 to the right of it will be that same value, but the plus version of it. So we go to our z-tables. Let's see, I'm going to want the negative one here. And we're looking for this z-value, the one that has the area to the left of it being closest to 0.05. So I just examine the z-table here. When is the area closest to 0.05? It's basically these ones. The book picks 2.58 for simplicity. You know, they're both the same distance away from 0.005. So technically the best z-score would be in the middle of those, I guess negative 2.575, but we'll only go to 2 decimals. So that's why they end up getting the 2.58 number here. This is negative 2.58. So that would be our z star for that. Or sorry, the z star is the positive of this. Right? This z-score is negative 2.58. And this z-score on the right is positive 2.58. Z star is the positive one. They just get essentially the magnitude of the z value. So z star is the positive one of the two. So that's how they get a z star being 2.58 when it's a 90% confidence interval. So I've got an example here that has a different confidence interval that we're used than what we're used to for an example for us to do together. This one right here is talking about a 98% confidence interval. Okay, so this question says a random sample of 50 cars in the drive-through of a popular fast food restaurant revealed an average bill of $18.21 per car. The population standard deviation is 5.92. Estimate the mean bill for all cars from the drive-through with 98% confidence. So we're using a small sample of what we got here to kind of extrapolate what the actual average would be. Okay, so let's just, as usual, the way I try to tell my students to do these questions is just go through it line by line, try to pick out the variables that you know, and then the variables that you end up writing down will inform you which formula to use. Because chapter 7 is broken down into a couple regions, and there's a couple different formulas, and it won't always be obvious which one to use. So once you write down all the variables, you'll be like, oh, I've got all the variables for this formula, so I'll use it in that formula. That's what I usually tell to my students. So, okay, so we've got a random sample of 50 cars. That's our n. Remember, that's the sample size, n. Revealed that the average bill was $18.21. So that was the sample mean, right? The mean of this sample that had 50 cars in it, that's $18.21. So that's our X bar. What else? The population standard deviation is 592. Remember, the symbol for population standard deviation is sigma. And we're looking for to estimate the mean with 98% confidence. So this isn't a Z star that we've got memorized. So we've got to come up with the Z star using the same method I just talked about. So let's do that first, and then we'll know what the Z star is, and then we could put it all in the formula. So we want the middle to be 98% of the data. That means there's going to be 1% in each tail. Right? If we've got 98%, that's 2% left over to divvy up amongst the tails. Cut it in half because it's symmetry, giving us 1% in each tail. And so we're going to be looking for this Z value, which has the area to the left of it being closest to 0.01. So we go to our Z table, we look for when is the area closest to 0.01, and that will give us, or tell us about our Z star. So 0.01, where's closest to 0.01? That would be this one right here, which is a Z-score of negative 2.33. So that's a Z-value of negative 2.33. That means this is a positive Z-value of 2.33. And so therefore, our Z-star is positive 2.33. Now we've got everything for our formula, and we can find the upper and lower bound for the confidence interval, the 98% confidence interval. Okay, the formula is X bar plus minus Z star times sigma over square root n, giving us 18.21 plus minus 2.33 times 5.92 over the square root of 50. Let me calculate the margin of error. Remember, the margin of error is the part to the right of the plus minus. The thing to the left of the plus minus is the point estimator. So confidence intervals are basically always a point estimator and then plus or minus some margin of error. So 2.33 times 5.92 divided by square root of 50. We're going to be getting 1.951. Okay, so we just add and subtract this value from 18.21. The lower bound ends up being 16.259. That's our lower bound. And our upper bound, 18.21 plus 1.951. That gives us 20.161. That would be our upper bound for the 98% confidence interval. So, most of the time, confidence intervals, they're talking about 90%, 95%, or 99%. But of course, now I've taught you guys how to do it for any percent that they give us. So I hope those are some good examples. And the last thing I want to talk about from this section is the sample size that you need to guarantee being able to use this estimation. Okay, so how large of an estimate, I'm sorry, how large of a sample is necessary to make an accurate estimate? Well, remember our formula was x bar plus minus z star times sigma over square root of n. This part is called our margin of error. Which I'll refer to as E. So that gives us E is equal to z star times sigma over square root of n. And if we're looking for how big of a sample size is necessary, we can solve this for n, and that will give us our answer. So essentially, we want to solve this for n. And that will tell us how big of a sample size is necessary given some margin of error. So how do we solve for n here? I guess first we can multiply everything by square root of n, giving us E times square root of n equals z star times sigma. We can divide by E next, giving us that the square root of n is z star times sigma over E. And then we can square each side. So we get n is z star times sigma over E squared. So this is how big of a sample is necessary to get however accurate of an estimate you're looking for. Oh, sorry, my mic was off for a sec there. So let's look at an example of using this formula to figure out how big of a sample size we need. It says a sociologist wishes to estimate the average number of automobile thefts in a large city per day within 2 automobiles. He wishes to be 99% confident, and from a previous study, the standard deviation was found to be 4.2. How many days should he select to survey? Okay, so let's pick out some stuff. A sociologist wishes to estimate the average number of automobile thefts in a large city per day within 2 automobiles. So that means he wants to get the number within 2 automobiles correct. So if the actual answer is 70, he would want the range to be 68 to 72. Right? The margin of error is basically how far away from the actual answer you want to be. So that's what they're telling us here. That's our E, right? The margin of error. He wishes to be 99% confident. This tells us what our alpha is for the formula. Or I'm sorry, our no, that's about the Z star. Sorry. So he wishes to be 99% confident. So that's the Z star. That's a Z star that we know, 2.58. And from a previous study, the standard deviation was found to be 4.2. Again, I wish they said population. And how many days should he select a survey? That's Rn, right? That's what we're looking for. So our formula is n is equal to z star times sigma over E squared. Plugging all this in, we get 2.58 times 4.2 all over 2 squared. And then I guess we'll round up to the next whole number because you don't want a sample size to be a decimal. You can't have a half of a sample. You can't have like 5.5 in your sample, right? That doesn't make sense. So we're always going to round up. I guess I should mention that here. You don't want to underestimate, just always overestimate. So always round up, even if it's like 10.1, round it up to 11. So what's this value give us? 2.58 times 4.2 divided by 2, and then I'll square that. We get 29.35, which will round up to 30. So in this case, we need to have at least 30 days in our survey to guarantee that we will have this accurate of an answer. And that should conclude section 7.1. So let's now move on to section 7.2, which is confidence interval for mean when sigma is unknown. Okay. So say we don't know the standard deviation of the population, right? That's sigma, which is going to be most of the time. Well, in that case, we're going to use the best point estimator for sigma, which is S, the standard deviation of a sample, rather than the standard deviation of the population. So when we don't know sigma, we use S instead. Okay, so when we don't know sigma, we use S instead. And this causes us to basically stretch the normal distribution a little bit using a family of curves with a certain degrees of freedom. And so we don't actually end up using z-tables for this one when sigma is unknown. Rather than z-tables, these are called t-tables. So I know it's a bit of a pain to have to learn how to interpret another table, but that's pretty much the best way to kind of understand this material, honestly. And we're then going to get the formula. Ends up being x bar plus minus, I'm going to call it t star instead of z star. And then instead of sigma, remember we're replacing it with s, so it's s over square root of n. This would be our formula for the confidence interval when sigma is unknown. Again, the differences between when sigma is known, is we're not using, we're not using a z-table anymore. We're using the t-table, and we don't know sigma, so we're using our best guess at sigma, which is s. And so that's how, when the problem gives you the sample standard deviation rather than the population standard deviation, this is the formula that you've got to use instead. And the same criteria actually hold from the last time. The sample needs to be random. And either n is greater than or equal to 30, or the population is normally distributed. When n is strictly less than 30. Okay, so let's look at an example, and within that example, I'll show you guys how to use the t-tables. Okay, so let's look at this question here from the book. A random sample of high temperatures for 12 recent Thanksgiving days had an average of 42 degrees Fahrenheit. Assume the variable is normally distributed. It has to say that because the sample is less than 30 here. And the standard deviation of the sample temperatures was 8 degrees Fahrenheit. Find the 95% confidence interval of the population mean for the temperatures. Okay, so we're trying to figure out, with a 95% level of confidence, what the actual mean for the temperatures on Thanksgiving Day is. And we're going to use a sample of 12 to try to essentially guesstimate the bounds for the population mean. Again, with 95% confidence. So let's just read through the problem like we usually do, and when we see a variable, we write it down. A random sample of high temperatures for 12 recent Thanksgiving days, that's our n. They had an average of 42 degrees Fahrenheit. The average of the sample, that's x bar. Assume the variable is normally distributed and the standard deviation of the sample temperatures was 8 degrees Fahrenheit. So the standard deviation of the sample, what's that? Remember, that's S. We don't know the standard deviation of the population. We know the standard deviation of the sample. So we know S, not sigma. And so that will tell us which formula to use. And it's a 95% confidence interval. Tells us that right here. We're going to need to know that when looking up the T star value. So hold on, I've got to get a T tables. Okay, so I've got a T table here. And on the left, it gives us the degrees of freedom. Degrees of freedom is n minus 1. That's how we find the degrees of freedom. It's always just n minus 1. So in this case, our degrees of freedom is, of course, 11. That's how we know which row to look up here in the T-table. Right, this says degrees of freedom, df, that's what degrees of freedom is. We find here, we've got our degrees of freedom is 11. It's always n minus 1. So that's the row we've got to look at. And it's a 95% confidence interval. So I see at the bottom here, this 95%, that tells us what column we're in. And so therefore, the T star we've got to use for this question is 2.201. And that's how you use the T-table. You figure out the degrees of freedom, which is n minus 1, and you combine it with whatever confidence level you're looking at, and that will tell you the T star. Okay, so we can plug everything in our formula now. Remember, the confidence interval is x bar plus minus T star times S over square root of n. So in this case, we'll get 42 plus minus our T star is 2.201 times S, which is 8 over the square root of n, that's 12. So we get here 42 plus minus, and then this is the value I'll calculate in my calculator, 2.201 times 8 divided by square root of 12, which is 5.083. So we do 42 minus this value, 5.083. It's our lower bound, 36.917. And our upper bound, we do 42 plus 5.083, which is 47.083. So we are 95% confident that the true average temperature on Thanksgiving Day is between 36.917 degrees and 47.083 degrees Fahrenheit. That's what we found out here. And in general, this is basically how we figure out the confidence interval for the mean when we don't know sigma. We could do another one together. We just find a good one. Okay, so in this example, it says a sample of 8 adult elephants had an average weight of 12,300 pounds. The standard deviation for the sample was 22 pounds. Find the 95% confidence interval of the population mean for the weights of adult elephants. So let's see here. Let's just pick everything out. We've got a sample of 8 adult elephants. That's our N. They had an average weight of 12,300. That's X bar. It says the standard deviation of the sample is 22. So since it's of the sample, that's S, not sigma. And we're looking for a 95% confidence interval of the population mean. So since we don't know sigma, we only know S. This is when we use the t-tables, and we use the formula X bar plus minus T star times S over square root of N. Let me copy the t-table that we had here. So what T are we going to use for this problem? In this case, our degrees of freedom is going to be 8 minus 1, aka 7. So we're in this row. It's a 95% confidence interval, so we're in this column. And lining everything up, we get 2.365 for our T star. And then we plug everything in that we know into the formula, and that will give us our confidence interval. So this gives us 12,300 plus minus 2.365 times 22 over the square root of 8. Okay, so 12,300 plus minus 2.365 times 22 over the square root of 8. That's 18.395. So 12,300 minus 18.395. It's 12,281.605. That's our lower bound. And the upper bound, 12,300 plus 18.395. 12,318.395. That would be our upper bound. And so we would be 95% confident that the true population mean of the weight of an adult elephant is between 12,281 pounds, and 12,318 pounds. Okay, and that should conclude this section. Pretty short section. Again, we're not a lot of formulas in this, and they're very similar to each other, so that's very, very helpful. So let's go to section 7.3. And this is on confidence intervals for proportions. Okay, so in proportions, it's basically a yes or a no, on or off. It's that same binary distribution, essentially. And so we're going to be estimating some population proportion. Maybe 81% of people said yes to the survey, or 39% of people said yes to the survey. We're trying to get what the population would say based on some sample survey, essentially. And so the formulas in these, basically, we are looking to find the true proportion, which is called P. That's the true population proportion, I guess I should say. So the population proportion, that's what we're looking for. That's called P. So we use a sample proportion as our point estimate. And then we're going to add and subtract some margin of error, like we normally do with confidence intervals. And the sample proportion, that's called P hat. So we're looking for P. We use a sample proportion, P hat, to kind of try to gain some insight about the population proportion. Okay, so the formula is P hat, right? Our point estimator plus or minus the margin of error. And the margin of error in this case, we're going to use the z-tables again. We go back to the z-tables. So it's z star times square root of p hat q hat over n. That gives us the lower and upper bounds. Just to make sure to define all this stuff properly, right? P is what we're looking for. That's the population proportion. P hat, that's a sample proportion. And that's x over n. The number of people that say yes over the total number of people is going to be the sample proportion of people that said yes. Q hat is the complement, essentially. So Q hat, right, P hat is the percentage of people that say yes. Q hat is the percentage of people that say no, essentially. And so Q hat is just always 1 minus P hat. And we find our Z star in the normal fashion based on the confidence level that we're given, or that we're trying to use. So again, very similar formula. We take our best guess, and then we do plus minus whatever margin of error is in the formula. And to find the margin of error, we've got to use a z-table, a t-table, depending on what is given to us. Okay, so let's look at an example here. This one says, a random sample of 150 assault victims in a large city found that 45 took no self-protection actions against the criminal. Find p hat and q hat. Oh wait, it's not as good. Never mind. I don't want this question. That's just coming up with the p hat and the q hat. Not a good one. Okay, here's a type of question I was actually looking for. A survey conducted by Sallie Mae and Gallup of 1,404 respondents found that 323 students paid for their education by student loans. Find the 90% confidence interval of the true proportion of students who paid for their education by student loans. Okay, so we're trying to figure out with some level of confidence what the true proportion of students that use student loans is. And we're using this sample to try to figure that out, to estimate it. So it looks like our n in this case is 1,404. And the number of people that said yes to the question was 323. That's our x. And we're looking for a 90% confidence interval. So our formula, remember, p hat plus minus z star times square p hat q hat over n. Well, p hat, that's x over n, the number of people that say yes over the total number of respondents. That's 323 over 1404. And we'll round it to 2 decimals or so, maybe 3, I don't know. 303 divided by 1404. Let's go to, I mean, in the book they just go to 2 decimals. Why not? Oh, I put the wrong number in. 323 divided by 1404. 0.23. And so if our p hat is 0.23, that means our q hat would be 1 minus 0.23, or 0.77. And now we've got everything except for the z star. But remember, for a 90% confidence interval, z star is 1.65. So we get, right, we just plop everything in our formula, giving us 0.23 plus minus 1.65 times the square root of 0.23 times 0.77 over 1404. So I'll just calculate our margin of error here, as I usually do. 1.65 times the square root of 0.23 times 0.77, all divided by 1404, which is approximately 0.019. 0.019. So we do 0.23 minus and plus this, 0.23 minus 0.019. That's 0.211 is our lower bound. And our upper bound of the true proportion with 90% accuracy is 0.23 plus that 0.019 value, which is 0.249. Or you can write them as percentages. So it's 21.1% to 24.9% would be our confidence interval. So we would be 90% sure that the true proportion of students that used loans for their education is between 21.1% and 24.9%. All right, let's do another example together. About these self-driving cars. A survey of 6,000 adults found that 58% say they would take a ride in a fully self-driving car. Find the 90% confidence interval of the true proportion of people who would say that they would take a ride in a self-driving car. I don't like how they phrased this question. I think it's a little bit lazy of grammar there. Oh well. So let's again find everything. We've got a survey of 6,000 adults. Found that 58% said that they would take a ride in a fully self-driving car. So they just gave us our p hat there. They didn't give us how many people that said yes. They just told us p hat. It's 58% as a decimal, that's 0.58. Remember, it's got to be a decimal, very important. And we're looking for a 90% confidence interval, which remember is a z-star of 1.65. And if p hat is 0.58, that would mean q hat would be 1 minus 0.58 or 0.42. So now we know everything needed for the formula. P hat plus minus z star times square root p hat q hat over n. So we get 0.58 plus minus 1.65 times the square root of 0.58 times 0.42 over 6,000. So what ends up being this number on the right? Approximately 0.009. Maybe we should go one more decimal. Oh, I put 1.5 instead of 1.65. I don't know how I did that. Let me just put the 6 in there. .0105. Let's do 0.011. 3 decimals should be fine. So we get 0.58 minus 0.011, which is 0.569. It's our lower bound. The upper bound is 0.58 plus 0.011, which is 0.591. As in percentages, that would be 56.9% and 59.1%. So we'd be 90% confident that the true proportion of people who would take a ride in a self-driving car would be between 56.9% and 59.1%. Hope that makes sense to everybody. And how big of a sample size do we need? Well, again, we could essentially solve our standard error here for n. Remember, the standard error, that's the part to the right of the plus minus, which in this case is z star times square root of p hat q hat over n. And so if we solve for n, we end up getting that n is p hat q hat times times z star over e in parentheses squared. And so this is the formula that we would need to figure out how big of a sample size we need in order for an accurate estimation. And again, then you round up. Always round up to the nearest n. Because very often this is going to be a decimal, but you have to round up to the nearest n. Okay. Let's do one of those examples together. A researcher wishes to estimate within 95% confidence the proportion of people who did not have a landline. A previous study shows that 40% of those interviewed did not have a landline. The researcher wishes to be accurate within 2% of the true proportion. Find the minimum sample size necessary. Okay, so 95% confidence interval. That's a z value of 1.96. A previous study shows that 40% of those interviews did not have a landline phone. So our p hat, that's 0.4. And therefore our q hat would be 0.6. The researcher wishes to be accurate within 2%. That's our error. As a decimal, that's 0.02. So we know p hat, we know q hat, we know z star, and we know e. Plug it all into the formula, round up, and that will tell us the minimum sample size necessary. So we'll get here 0.4 times 0.6 times 1.96 over 0.02 squared, whatever the heck this number is, and then we round it up. 0.4 times 0.6 times 1.96 divided by 0.02 squared. We get 2304.96 rather, which we round up to 2305. And that would be, in this case, the minimum number of respondents needed to get an accurate estimation. Okay. And the last section to talk about in this chapter is 7.4, where we're talking about looking for confidence intervals for variances which remember is sigma squared, and standard deviations, which is sigma. Okay, so for this last series of confidence interval formulas, we need another type of chart, again, unfortunately. They're called the chi-squared charts. And I'll give the formulas here first, and then we'll talk about how to use the table and come up with some answers. So the formula also looks a little different. There's no like plus minus and then a value because there's two different values that we need to use from the chart. So the confidence interval for variance, remember variance is sigma squared, it's between these two values, n minus 1 times s squared over chi squared left, and the lower bound is n minus 1 s squared over chi squared right. That's for variance. And the confidence interval for standard deviation is sigma, so it's just the square root of these on each side. That chi, that's a Greek letter. Looks like a curly X kind of. And that will give us our confidence interval. So basically what we have to do here is talk about how to use the chi-squared charts. Let's look at an example, and then we'll talk about that when we get there. Right here. This question which says, a study of 30 women found the standard deviation of their ages was 5.2 years. Find the 95% confidence interval with the variance for the age variable. Assume the variable is normally distributed. So a study of 30 women, that's our N. And in that sample, they found their standard deviation to be 5.2 years. So that's our S. And we're looking for a 95% confidence interval for variance. So that's sigma squared. I guess we could find both though. So we've got to come up with the, we already know N, we know S. The only other thing we need for our formulas is the chi-squared right and left values. So hold on real quick, let me get a chi-squared chart and we'll go through that. Okay, so I've got a chi-squared chart here. Let me show you guys how to read it. So our degrees of freedom, again, is always just n minus 1. In this case, 30 minus 1, that gives us, we need 29 degrees of freedom. So that's this row. But then we've got to look at two different columns. And it can be a bit confusing. Let me show you all what to do. It's definitely really helpful to draw a picture every time. So we want a 95% confidence interval. Again, meaning that this inner percentage is 95%. So if we've got 5% left to divvy up, that means we want 2.5% here and 2.5% here. So in decimal form, this value to the area to the left of this value is 0.025. The area to the left of the value on the right it's got what? It's got 95% and 2.5% to the left of it. You've got to add these together. That's 97.5%, right? And if we move the decimal 2 spots to the left, aka 0.975. So we got to look up the columns for the areas to the left of each of these. This one is 0.975. It's also always 1 minus the other one, is the area that we need to look up. So let's see here. We look for the 0.025 column and the 0.975 column. And the one on the left is the chi-squared left value. The one on the right is the chi-squared right value in each respective row and column in the intersections. So in this case, we get that chi-squared left is 16.047, and chi-squared right is 45.722. And that's what we need to put in for our confidence interval formula for variance. So remember, the formula is first variance, rather. It's n minus 1 times s squared. The upper bound is over chi-squared left. I know that could be definitely confusing because it's on the right side. The left and right comes from when you're looking up the tables, the values in the table. It's referring to the left value and the right value. At least that's how I remember coming up with them. And our lower bound is n minus 1 times s squared over chi-squared right. So let's just plug everything in here. And that will tell us our upper and lower bounds for the variance. N minus 1, that's 30 minus 1, that's 29, right? So we get 29 times s squared. S is 5.2 over chi-squared right, which is 45.722. And the upper bound, it's going to be 29. That's the n minus 1. It's essentially degrees of freedom. You could even put df there instead, because df is n minus 1. Anyway, times 5.2 squared over chi-squared left, which is 16.047. And that will give us our confidence interval for the variance of the population. So the lower bound, 29 times 5.2 squared, and then divided by 45.722. We end up getting 17.151, I guess. And our upper bound, I can, it's the same numerator, and the numerator I calculated to be 784.16. And this time we've got to divide 16.047. We end up getting 48.866. And that would be our confidence interval, what percent, not the 95% confidence interval for our variance. And of course, the standard deviation, you just take the square root of each side. So let me square root this one. Just going to put answer to get the fully accurate version. But I'm going to round anyway, so we end up getting 6.99 here. And our lower bound, it's square root of this answer, which is approximately 4.141. And that would be the confidence interval for the standard deviation. Okay. And so in general, this is how to find the confidence interval for variance and standard deviations. We've got to use these chi-tables, called the chi-squared charts, or chi-squared, whichever you want to say. So let's do another example together, and that should round up this video, I would say. Okay, so here I've got a question that says, find the 90% confidence interval for the variance and standard deviation of the ages of seniors at Oak Park College if a random sample of 24 students had a sample standard deviation of 2.3 years. Assume the variable is normally distributed. So we're looking for the 90% confidence interval for standard deviation and variance. And the sample of 24 students, that's our N, had a standard deviation of 2.3 years, that's S, the standard deviation of the sample. And again, since we're looking for sigma squared and sigma, we use the chi-squared tables for this to figure out the value that goes right here in the denominator of these formulas. So our degrees of freedom, remember that's always just n minus 1. So it's 24 minus 1, aka 23. So we're in this row, and it's a 90% confidence interval. Let me draw a picture here. So the inside will represent 95% of the sample means, essentially. And so we would have 5% left to divvy up amongst each tail. So this value, we want 0.05 to be to the left of this. And this value over here, we want 95% or 0.95 an area to the left of. Right, the area to the left of this value over here is, it's 95% of the area is to the left of this, aka 0.95. So the columns we look up, this column and this column. Intersecting everything, we get these two values. That's our chi-squared left and our chi-squared right. So it seems chi-squared left in this case is 13.091. And chi-squared right is 35.172. Plug everything into the formulas, and that will be our answer. So for variance, I've got our formulas here. And plugging everything in, what do we get? N minus 1, that's 20. Oh, I forgot the s squared here. That's 29 times, I'm sorry, 23 rather, times s squared. S is 2.3, so that's times 2.3 squared, over chi-squared left, which is 13.091. Over on the left side, we get 23 times 2.3 squared, over chi-squared right, which is 35.172. And then we just got to calculate them. So what's this numerator? 23 times 2.3 squared. And then divided by 35.172. So our left side is approximately 3.46. Let's go to two decimals. And the right side, we get 121.67. That was the numerator. That's 23 times 2.3 squared. And dividing 13.091, we get approximately 9.29. So that would be our confidence interval for the variance. And it's also asking for a standard deviation, which of course is just the square root of each of these. Right, sigma is the standard deviation. So let me square root this answer. It's 3.05. The other one, square root of 3.459285796 is approximately 1.86. And so that would be the confidence interval for our standard deviation. And that should conclude our review of Chapter 7. Again, just a brief overview. What we talked about here. Right, we've got two different ways that we could look for the confidence interval for mu, aka the mean, or population mean. Either we know sigma or we don't know sigma. When we know sigma, we use the z-tables. When we don't know sigma, we use the t-tables. And we use s rather than sigma, because that's our point estimate for sigma. We looked at proportions, where the formula is p hat plus minus z star times square root p hat q hat over n. And the last one, we looked at the confidence interval for variances and standard deviations. And that's the chi-square tables. And the lower bound is n minus 1 times s squared over chi squared right. And the upper bound is n minus 1 squared over chi squared left. So I hope this was a good review for you guys. Please, again, always feel free to email me with questions. And have a great rest of your day.